Here's something most people never think about. Size matters in networking, and it matters more than you'd expect. Every message you send across a network has a size. Some are tiny, a few bytes signaling yes or no. Others are massive, megabytes of video, data, or files. And that difference, it completely changes how the network behaves. Think about it like this. Imagine you're moving to a new apartment. You could pack everything into one enormous moving truck, make a single trip, and be done. Or you could make 20 trips in your car, carrying a few boxes at a time. Same stuff, completely different experience. That's exactly the choice every network system makes, thousands of times per second. How much should we send at once? Networks don't experience your intent. They don't know you're trying to load a web page or stream a video. Matter of fact, all they experience is volume. Bits moving through wires, filling buffers, consuming bandwidth. So when we talk about message size, we're really talking about one fundamental question. How much are you trying to say at once? Message size is the total amount of data in a single message, everything from the actual content you care about to all the structural overhead that makes the message work. It's not just your email text or your video stream. It's also the headers, the metadata, the control information, all the addressing and instructions that tell the network how to handle what you're sending. From your perspective as a sender, message size is about grouping. How much information do I bundle together before hitting send? From the network's perspective, message size is about cost. How much work will this take? How long will it occupy my resources? How much memory do I need to set aside? Here's a better way to visualize it. Think of messages like cargo shipments. Sending many small packages gives you flexibility. If one gets lost, it's not a big deal. You can reroute easily. You can squeeze through tight spaces. But it's inefficient. Lots of packaging, lots of separate handling, lots of overhead. Sending one massive shipment is efficient. You amortize all that packaging cost over a huge amount of stuff, but it's risky. If something goes wrong, you lose everything. And you need the infrastructure to handle something that large. Networking constantly balances between these two extremes. Here's where it gets interesting. Messages are rarely transmitted as single, uninterrupted units. Large messages get split up during transport. The network breaks them into smaller chunks, sends those chunks separately, sometimes even along different paths, and reassembles them at the destination. Small messages sometimes get combined with others, batched together to reduce overhead. But these are just transmission details. They don't change the logical size of the message itself, the amount of information you decided to send as one unit. Most protocols define maximum message sizes. These aren't arbitrary. They exist to protect networks and endpoints from being overwhelmed. When a message exceeds those limits, it must be divided, restructured, or flat out rejected. And here's the thing. Endpoints choose message size deliberately. Application developers decide how much data to include in a single message based on three competing priorities: efficiency, reliability, and responsiveness. Small messages move quickly. They need minimal buffering. If something goes wrong, they're easy to retry. But sending many small messages means more overhead, more coordination, more work for the system. Large messages reduce that overhead. You spread the structural cost over more actual data, but they're slower to transmit, harder to retry if they fail, and more vulnerable to disruption. If part of a large message gets corrupted or lost, you might have to retransmit the whole thing. This is the eternal trade-off. Message size influences network performance more than almost any other property of a message. First, latency is affected because a message can't be processed until it's complete. If you're waiting for a 10 megabyte message to arrive, you're waiting for every single bit of those 10 megabytes. The larger the message, the longer you wait. Second, throughput is affected because large messages occupy network resources for extended periods. While a massive message is moving through, smaller messages have to wait in line. Third, memory usage is affected because incomplete messages have to be buffered somewhere. Your system has to set aside space proportional to the message size, holding it until everything arrives. Fourth, reliability is affected too. The larger the message, the more opportunities for something to go wrong. A single corrupted bit, a single lost packet, a single timeout, any of these can derail the entire message. Last but not the least, message size affects fairness. Large messages can monopolize shared resources, blocking everything else. Small messages can weave through congestion, finding gaps and moving ahead. It's like highway traffic. A convoy of trucks takes up the whole road. Motorcycles can slip through. It's worthy to mention that message size is relative. What counts as large depends entirely on context. A 1 kilobyte message might be huge for a real-time control system where every millisecond counts. That same message would be trivial for a file transfer system moving gigabytes of data. The network matters. The protocol matters. The environment matters. When messages are too large, they get broken into smaller transmission units. This introduces coordination overhead. Now the system has to track multiple pieces, reassemble them in order, and handle the possibility that some pieces might get lost. Moreover, message size shapes buffering behavior. Receivers have to allocate memory proportional to the size of messages they expect. If you're designed to handle 1 kilobyte messages and someone sends you 100 megabytes, you're going to have a problem. Poor sizing decisions lead to memory pressure, buffer exhaustion, and system crashes. Message size also affects error recovery. Retrying a 100-byte message costs almost nothing. Retrying a 10 megabyte message costs everything you spent transmitting it the first time. This influences how systems design acknowledgements, checkpoints, and retry logic. Finally, message size reflects application intent. Are you optimizing for responsiveness or efficiency, interactivity or bulk transfer? Sending many small messages says, I need quick feedback, I want to react fast, I value control. Sending fewer large messages says, I'm moving a lot of data, I care about throughput, I'm willing to wait. These characteristics add up to shape real-world behavior in ways you see every day. Congestion emerges when large messages pile up in transit, filling buffers and queues. Latency spikes when messages take too long to complete, keeping applications waiting. Head-of-line blocking occurs when a large message prevents smaller ones from being processed. Everything gets stuck behind the slow truck on a one-lane road. In distributed systems, message size decisions often determine whether the system stays stable under load or collapses. Oversized messages can trigger cascading failures. Undersized messages can overwhelm systems with pure coordination overhead. So many small messages that the system spends all its time managing them instead of doing useful work. Message size also intersects with security. Very large messages can be weaponized to exhaust memory or processing capacity. Attackers use this technique deliberately. That's why strict size limits are often a first line of defense. Understanding message size explains so many real-world design choices. Why do streaming systems send data in chunks instead of all at once? Message size. Why do APIs impose payload limits? Message size. Why are retries selective about what they resend? Message size. Why does batching exist? Message size. It's not a tuning parameter you adjust at the end of a project. It's a fundamental design choice that shapes everything downstream. Performance, reliability, scalability, cost. Messages carry meaning. Boundaries define completeness. Size defines cost. When you understand message size, you understand why networks feel fast or slow, fragile or resilient. You understand why some systems handle load gracefully while others collapse under pressure. It's a decision, a trade-off, and a consequence. That is message size.